Okay, so there's a couple of forms that I'm gonna provide you this lecture in. Yeah, you may notice that they unfortunately misspell my name, and I'm afraid they'll screw it up if I ask them to change my username. So I'm just going to use from now on. That's my name. Okay, it's just easier. Trust me, I've dealt with ICID before. It's just easier to do it that way. Okay, I want to open the syllabus because you guys had some questions on the syllabus. Okay, first of all, number one, there is a version of the syllabus on here from August 27th. If you got one that's early, if you logged onto Blackboard earlier than that, you might have a slightly different version of it that has that some of the dates might be a little bit different. Okay, so on the syllabus, it says that we're going to have that your grade is going to be based on Word. Unfortunately, on my machine takes a while, especially when I'm doing this. Takes a while to kind of wake up and let me minimize or open pages. Um, um, First of all, in terms of like what your grade is going to be based on, it's going to be based on assignments, homework assignments. I think it's 30%. Once this thing is working, we'll be able to, here we go. Okay, good. We'll be able to scroll there. Okay. Your grade is going to be based 20, let me get to that part. There it is. Just went by. Okay, 30% is based on homework. 20% is based on each of two exams, right? 20% for the first exam, 20% for the second exam. 10% is class participation. Well, what is class participation? Well, it's not just showing up here. It's also, I'm going to have to send around an attendance sheet because I'm required to. I'm not going to probably most classes I won't take a physical attendance, but for these first two sessions I need to because I'm required to fill out an attendance roster for the registrar because people that are here on visas or have scholarships and so on and so forth, or have financial other forms of financial aid, we have to confirm that they're attending class. So I'm gonna be, before we're done, I'm gonna hand out a piece of paper. Make sure you put your name and email address on it before you leave. So 10% is going to be class participation. Part second is going to be what we do here. The other part is some of you may have noticed that if you email me a question over the last 2 weeks that I thought was relevant to stuff that other people would be interested in, I probably suggested, I didn't do this every time, but I probably suggested, well, instead of sending it just to me, post it on the discussions board in Blackboard. Okay, so did I tell you guys to do kind of an introduction for yourselves on Blackboard? I didn't really want to know anything about you guys. I did that because I wanted you to start to get familiar, to use that discussions group. And it's really valuable because then you don't have to wait for me to, wake up to the fact that you send me an email or something like that. And I get a lot of emails, I might miss it and so on. A lot of times other students will give you feedback and help you out with stuff. And in fact, if there's a problem, I'll notice and I'll figure out, well, gee, this stuff's not. If I see a lot of people responding to the same thing or have an issue with the same thing, I'll wake up and I realize, yeah, I'm going to have to go over this again. So I would encourage you, if you're shy, don't worry about it. You can always email me. I have no problem with that if you prefer to do that. But I think it'll help everybody out if you posted a discussion groups. It'll also help everybody out if you know the answer to spend a little time and type out an explanation or maybe put down a link or something like that that might explain the question or something like that, answer to the question. So part of your class participation is going to be what goes on here. The other part is going to be what goes on in the discussions group. Okay? And trust me, it'll turn out to be a valuable thing. You'll see as we progress. The last part of this is 20% for a final project. Well, what is a final project? I'm going to provide you with data. Well, we're going to work either I will provide you with databases, which I will for everybody. I'll provide databases for everyone that you can use to extract some information from, do some descriptive statistics, run some statistical tests. It'll be up to you to decide how you're going to use it. There's something called the New York City Community Health Survey. How many of you guys know about that? New York City Community Health Survey. It's a couple of you guys know. Were you involved with it or something like that?
Is it the same one with the New York City Department of Health?
Yeah, but they call up. It's a phone survey.
Oh no,
and
I just know the paper one.
Okay.
They have a paper one that is for like high school students. I don't
Oh,
know.
no, no, no. This is actually what they do is they call up, they randomly call, I think something like 8 or 10,000 people or something like that around the city of New York every year, randomly selected people around the city, and they put them through a grueling questionnaire. I don't understand how to get 8,000 people to do this personally, because there's like 150 questions or something like that. And they include stuff like, gender, whether you smoke, how much, what kind of dietary questions, mood questions, like psychological questions, and so on and so forth. So I guess they get enough volunteers to answer these questions online. Maybe they use, I don't know, they might use some sort of endorsement or something like that. I have a home that has a lead main coming into it from the street. So the city sends me sample bottles because they want to know, they're required by the EPA to have point of use samples for lead in New York City. So they send me a bottle every 6 months to take a water sample from my house and send it to them so they can satisfy that point of use sampling requirement. And for that, they take $100 a year off my bill, right? So they may have some sort of inducement like that to take part in this survey. Okay, I work in the water treatment industry during the daytime, air quality and water testing and so on and so forth. And it's a typical case of like, the shoemaker's kids always have to wear shoes, right? I have a lead main coming into my house for the last 25 years, but that's a whole nother issue. So I'll get around to replacing it one of these days, I guess, maybe. So at any rate, that project will be something that you'll do on your own from the data I provide to you. Now, if you're taking another course where by the end of this course, you see that there's an opportunity for you to cross over what you're doing here into that other course, or you have other data that you have available to you at work or something like that, you can use that instead. Now, a lot of times, a lot of people feel uncomfortable, and that's good. But the form that's going to take is a poster presentation. Remember the science fair? You had OTAG, and you put stuff on the OTAG and stuff like that. Your objective and your descriptive statistics and your analysis, your conclusions, and so on and so forth. You put that on. You won't actually mount it on OTAG. You'll print it out, and then we'll have boards that you can stick it onto. You can do that. Or usually, because there's always people that are very shy about this, and because the class is decent size and it's just me here, and usually what I do is I give you 5 or 10 minutes to orally present what you have there, each person. You can instead take a third exam. Okay, that'll be up to you. We'll see as we get to the end of the semester. I hope you guys will be comfortable enough to maybe try something like this on your own, right? So I grade it pretty liberally, but I know there are people that have issues with public speaking and stuff like that. Okay, so that's the grading thing. Now, as far as the homework is concerned, in here it has a policy that if you're late on the homework, it's 10%, I think, each week or whatever. You penalize some amount. I'm not even going to go back there and read it. Okay, and inevitably, what happens is there are always students that are late on the homework, and I got to knock points off of them, and then they fall behind, and so on and so forth. I have my own policy on that that's not in here. And that is, if you make an effort to do the homework before it's due, like in other words, whatever, I think this one's due like on Monday. Monday or Sunday at midnight or something like that. If you make an effort to do it anytime for the rest of the semester, you can go back and you can try it again. Okay? So, and each time you try it, presumably you're going to higher score. Right? This particular homework is a little bit different. In this particular homework, you have to wait for me to grade it, right? Because I have you uploading documents, those Excel files. I have to go to each one of them, open them, look at them, and grade them, and so on, right? So you have to wait until I get to that homework. And usually I wait until, there's at least enough of them to make it worth, rather than doing one at a time every hour. I wait till there's enough of them worth doing, right? So you have to wait for the grade on that. Most of the ones for the rest of the semester will be auto grading, so you'll know right away if you got the right answer or wrong answer on something, right? So you'll have an opportunity to go back there and do it again. And I love when students, first time they do it, get 50%. Second time they get 60%. Third time they get 70%. Fourth, and do it 5 or 6 times, and then they finally can do the entire homework. I love that. That's great. So if you're concerned that first time out you don't get a you don't get a great grade on it, don't worry about it. The objective is that I want you to keep up, because it's kind of course where if you don't keep up, things can like really snowball on you, make it much more difficult. Yes.
In terms of because I know for this one it has unlimited attempts.
Yeah.
Before we hand it in, let's say we've already attempted it like 3 times. Do you only grade the most?
I only grade if I don't get to it in time. I only grade the last one.
Okay.
Yeah, because it doesn't matter. The other two don't matter if you presumably got lower scores on it, right? So what if you look at the flip side of this coin? There's no reason for you not to get 100% on homeworks. So 30% of your grade is 100%, right? So it really pays to do these homeworks and at least try them initially, so that you earn the opportunity to go back there and do them again without losing points and so on. Yes.
Okay, so the due date is on the 18th, right?
Yes.
So should I submit my assignment today?
Yes.
Right?
Yeah. You can do it again before the 18th if you want.
Grade it?
Yeah, I'll grade it.
And then give it back to me.
Yeah, like I said, you'll see me as we go on every couple of days. I'll hit them and I'll grade them all. So before the 18th, you'll have a couple of opportunities, but it doesn't really matter, because even after the 18th, you can resubmit it and get a higher grade. Right?
Just the questions you got.
Yes. Well, the point is, I want you to learn the stuff, right? I don't want you to be penalized for doing the homework. I want you to be rewarded for doing the homework and getting it right eventually. Not necessarily first time, but eventually getting it right. Yeah. And this, a lot of this stuff that we're doing in the beginning here, that you're going to find you have an advantage there too, because stuff we're doing at the beginning here, when you look back at this in 4 or 5 weeks or something like that, you're going to say, oh, geez, that was so simple. Why didn't I understand how to do that? And it's because first time you're looking at this stuff, first time you're using SPSS, first time you're using some functions in Excel and so on and so forth that you have never worked with before, it can be a little intimidating. But then as we go through the semester, the stuff we took earlier, because the other stuff builds on it, it's going to fill in a lot of gaps for you as we go along. So, that's really where we stand with this stuff. So any other questions about the syllabus? Yes.
With grading, right?
Yes.
You have week 3, self-test 1, week 1, self-test.
Oh, okay. You know what those are? Every once in a while, if I put in a video or material in there, sometimes I'll add in like a little self-test. Like now that you read the material in the book, here's a couple of questions just to see if you know it. That's only for you. It'll grade right away, and that's only for you. It's not the only thing that's graded is the actual assignments themselves, not any self-tests or anything like that.
So you don't have to.
Huh? You don't have to. Nope. Completely voluntary. Just like if you want to if you want to tune into the help session or review session on Thursday, that's completely voluntary also, right? You just join and leave whenever you want. Yes.
You have points allotted to them.
Yeah, like 1 or 2 or 3. Yeah, because I have to. That's the way it works in Blackboard. I can't do it without making points for it. You know what I'm saying? Like in other words, it's usually only a point per question or something. It's not like 80, not like on an assignment that's 100%, right? Those self-help things are usually a point per question, because I got to put in a point value for it to work. Yes.
And then, the exams, they're going to be in class.
They're going to be in class. Yes.
Is it like multiple choice? Do we have to?
There'll be a combination of multiple choice and problems. Okay, most of the multiple choice stuff, probably, if you go back through the PowerPoints and lectures and stuff like that, and some of the exercises, that's where they're drawn from. And the problems will be probably pretty similar to the homework. Right now, I will maybe change things around a little bit, or throw something in there to challenge you a little bit. But no, hopefully I won't throw too many curveballs or anything like that, right? They'll be pretty straightforward. Yes.
What's the postmortem?
Oh, that's just to go over the test. If you want to hang around for a little bit after the test, for a half hour after the test, we can go over it and stuff like that. Or I can do that online afterwards, So we'll figure it out. Depends on how long you spend on the test. Okay, if the test takes, hang on a second here. Let me just check something here. What are our official hours for this class?
110.
110? They told me it was 120. Oh, okay. No wonder there's so many of you. 110 to 340. Okay. So what is that? That's 2.5 hours. Okay. Well, but like I said, if I'm to try and design a test so everybody can get it done in 2 hours, then we'll have a half hour to like after everybody submits it. Most of the tests will be probably done on Blackboard. So you'll do it on Blackboard, submit it on Blackboard. So hopefully we'll have a half hour to go over it and stuff like that. That doesn't always work. A lot of times I underestimate how long it's going to take, and yeah, everybody's got their own concerns, and like some people like to go over it 97 times or can't give up on it, and so sometimes that doesn't work out that well. And that happens, we'll do it online. We'll do a postmortem online. But I like to go over the test because what's the point of taking a test if you don't learn anything from it, right? So eventually we get to that point. 110, eh? Okay. No wonder you guys are old. Well, I say to myself, wow, these people really showed up early today. Well, you know what it is? For some reason, this is an odd semester with the room assignments and the times and stuff like that. And usually I'm teaching at night. And apparently the hour, the class start times are different during the day than at night. At night, they always start on the hour and they end 10 minutes before the hour. So now that I know that, I'll make sure I'm here at 1:10. Okay, so so the material each week is going to be in the weekly session for that week. Okay, usually I try and make them available like at least a day or so ahead of time, usually more if I can. And I'm going to open up this PowerPoint. I'm going to go through this PowerPoint to start off with. Okay, so today we're going to look at basic principles in descriptive statistics, calculation, ways of describing different kinds of statistics. And part of what's important here is that you may have noticed the first few questions on the homework assignment were about the types of data. Okay, and the reason why those first few problems were about the type of data is because the way that you describe data is going to be contingent on the type of data is, whether it's categorical data, ordinal data, numerical data. Our description of that material is going to change based on that. Okay, so we'll cover stuff we started calculating last week. We talked a little bit about bar plots and histograms, mean, median, mode, and so on and so forth. We started to talk about that. And now we're going to really start to apply it. Okay, so a little bit of vocabulary here. Probably mentioned this before, but now it's kind of like this is mainstream for today. When you talk about a population, talking about everybody in that population group. Population could be the population in the United States. It could be a population you define more narrowly. For instance, the males between 40 and 45, with a BMI between 25 and 30. Right, much narrower definition of a population, but still, if you count everybody that fits that description, they're a population. We rarely, if ever, really get to work with numbers that involve populations. Unless we're in the business of census taking, we can't afford to go out and survey everybody in a population usually. So what we do is we take a sample, take a subset from that population. That's a sample. Anytime in the future that we start discussing populations and samples, and we start doing statistical calculations involving them. When we're talking about a population, we typically use Greek letters. So, for instance, if I talk about population mean, you'll see me use the symbol mu for mean of a population. On the other hand, if I'm going to take a random sample from a population, 100 people, let's say, and I take the average of that sample, then I'm going to use X bar. I'm going to use alphanumeric characters for describing that. Okay, standard deviation. I'll just use SD for a sample, but I'll use the Greek symbol sigma for a standard deviation of a population. So anytime you see that, you'll know whether I'm talking about a sample or a population. Big difference between the two of them. So, for instance, if I take a sample of 100 people, and I find the mean of those 100 people, let's say I'm taking their weights, and I find the average weight is 150 pounds. Am I really interested in the average weight? That's going to be X bar is equal to 150 pounds. Am I really interested in the mean weight of that sample? Right. The only reason I'm taking finding the average weight of that sample is because I want to use it to predict what the average weight of the population is, mu. So that sample, all of these sample statistics are only, their whole goal is to help you estimate what the population is like. Not the sample itself is not the end. It's really your estimation of the population. So, but most of the time we're going to be working with samples because that's the only way that this is going to be possible. Okay, a record or observation, that's an individual person's weight. A record could include a number of variables, person's weight, person's age, person's marital status, and so on and so forth. Yes?
Can you move that box that's on the...
Oh, yeah, sure thing. I didn't realize that. You see, you guys got to tell me about this stuff. I didn't look back, did I? Come on. Let me get this out of the way. You know, there's probably something back here that's getting in my way. Oh, there we go. Let me get this out of the way, too. Okay, that's better, right? So now, here you've been staring at this the whole time, and you didn't tell me about it, right? I'm facing this direction. It's doing the same thing.
It didn't show up.
Oh, it didn't show up on your screen? Oh, you know why? Because you clicked it away, right? You notice I had to click OK on that. I had to agree to something there. That's why that box was still there. You did it because you had the patience to wait for the box to come up. I turned back around and was connecting to it at the time. Okay, so descriptive statistics. What are descriptive statistics? They are a description of that data that you've collected, summarizes it. Could be numerical summary, like the mean, the standard deviation, the range, or something like that, or it could be a graphical representation, like a bar chart or a histogram or a pie chart or something like that. We're going to play with some of that right now. And that's descriptive statistics. That's what we're mostly concerned about today. Inferential statistics is statistics where you are applying the statistics the data you collected and the statistics you worked with in order to infer something about the population or in comparisons to another population. For instance, do Frenchmen have higher rates of Frenchmen have lower rates of heart disease than Americans do, right? Something like that. You would use, that's inferential statistics. Another situation where you're testing a drug, a placebo versus the actual drug itself, its effects. Okay, variables. We talked about variables, three basic kinds, right? Nominal, ordinal, and quantitative. Or you're going to hear me and everybody else use a lot of different terms to say the same thing. Nominal means just a name, right? Nom is Latin for name. Nominal, it could be a gender. Gender happens to be a binary category, right? It's male or female. A lot of others have more than one group. For instance, hair color has a number of different options you could have for that variable. The variable is hair color, though. Okay, that's a name. Marital status, race, so on and so forth, all nominal variables. Okay. A special form of a nominal variable is called an ordinal variable. An ordinal variable is a number or a name that represents something that is really being named but has order of some kind. For instance, if I were to say a grade, for instance, right? My grading might be fair, good, poor, excellent, so on and so forth, right? Poor, fair, good, excellent, right? So the grade is a name. It's a word. It's a name, but it has order. Poor is not as good as fair. Fair is not as good as good. Good is not as good as excellent. But it doesn't necessarily have a value, right? So in other words, you don't know for sure what numerical grade good might represent, right? Or fair might represent. And you don't know if the difference between good and excellent is the same as the difference between poor and fair, right? We don't know how to categorize that. It can be a number scale where the numbers really represent levels or names. The pain scale, 1 through 10. Most pain is 10, least pain is 1. And for instance, your 5 may not be the same as another person's 5, right? But there is a difference for you between 5 and 6 and 7 and 8, right? That's your personal difference. And even for you, you couldn't tell me for sure whether the difference that you're relating to is 5 to 7 in the physical world, in the chemical, biochemical world, something like that, really is the same as what you would report as the difference between 3 and 5, right? There's no way for you to really quantify that. You just know one is more than the other, in your judgment. Okay, so that's very different than the third form of variable, which is quantitative. Quantitative could be termed numerical, discrete, numerical, continuous, scalar. SPSS uses the word scalar for quantitative variables. And that could be something like weight, BMI, so on and so forth. Then in those scales, you know that if a person's temperature is 98 degrees, another person's temperature is 99 degrees, it's 1 degree more. And the difference between 98 and 99 is the same as the difference between 100 and 101. It's 1 degree, one degree on a certain scale, right? And it's a continuous scale. Could be 98.3, could be not. Even when we talk about blood pressure, right? Traditionally, you just round it off to the nearest millimeters of mercury. So somebody's blood pressure is 120 over 80. It's not 120.111 over 80.09, right? So even though that literally is what it could really be, right? So that is a quantitative scale or numerical variable, where by nature, a lot of times you'll hear people refer to a special kind of quantitative variable called the discrete quantitative variable. Okay, so that's something that by nature is a integer. For instance, the number of siblings that you have, right? You got 2 brothers and 1 sister, you got 3 siblings, right? The number of parents that you have, the number of cigarettes you smoked today, right? That's a discrete numerical variable. I put it in the homework. I bring it up here because inevitably it's going to come up somewhere in your future. But as far as I'm concerned, forget about it. It's just a numerical variable. I mean, functionally, it's a numerical variable. And one evidence of that is that you don't see it as a choice on SPSS, right? If it were important that you really distinguished it, it probably would wind up there, I would think. Okay, ordinal, nominal. So nominal and ordinal kind of like are similar to each other, and typically you describe that by using frequency tables. So, for instance, a nominal variable, male and female. How would you describe a population's gender? Well, you'd say, you got 53 males and 107 females, right? That's all you would do is count the frequency for each one of those. Hair color. Oh, we got 27 brunettes, 87 blondes, and so on and so forth, right? Frequency. How would you display that data? Well, you could display it in a number of ways. One way is you could buy a bar chart. We looked at bar charts last week, right? Or you could use a pie chart, right? Gender. You could draw a circle, and the area of the wedge in that pie that represents males would represent that percentage of males. You could do it as frequency, or you could do it as percentages. SPSS, you'll see they give you that option. Here's a couple of pictures. Treatment and control groups, typically both same number of people. Outcomes, mild, moderate, severe. Again, it's ordinal data, but that's kind of a form of nominal, right? Because in other words, how many people are in the mild group, moderate group, and severe group, you display as a bar chart or as a frequency table. Pie charts. That is bad joke. I'll skip the bad jokes. I'll skip the bad joke. I'll only tell you the good jokes.
Hey, we're laughing.
Oh, okay, there you go. Okay, 4 students receive an A. Okay, let's see. And proportion. When you deal with frequencies, you also deal with proportions. If I told you 40 were males or 60 were females, then 40% of the population obviously is male. Okay, and you can use those as a substitute. So it's pretty dry stuff so far, right? Okay, we're gonna have some fun with it though. Yes.
With frequency, is that always it's just a
count?
Frequency is a proportion.
It's just it's frequency is a count. Okay. The number of people, frequency and number of people. On that precedence graph, the height of the bar and the numbers guy. I couldn't get Excel to let me put the a name on the y-axis, right? But if there were a name there, it would say frequency. Frequency is the number of presidents that that bar represents. That's the height of the bar. Now, instead of that, those bars, I could have put 0 to 100, and the bars could have been the percentages. Each bar could have been the percentages of presidents that were represented there. If there were 50 and there were 2 presidents in one bar, that would be 4%, that bar. Next bar might be 15%, and so on and so forth. But a lot of times you'll see frequencies converted to percentages instead. Well, it'll be clearer when we actually play with it. Now, quantitative variables, numerical variables, there's a number of ways that we might display that. One is histogram, right? Histogram we know is one of those, a special kind of bar chart, where the bars butt up against each other so that the bar represents a range. If we're talking about ages of a population, one bar might, or presidents, right? And presidents, each bar represented 5 years. A president that was between 40 and 40, just before 45 years, goes into this bar. President that's 45 years to just before 50 years goes into this bar, and so on and so forth. So histograms, typically those bars represent a range of values, and the height represents the number of people that are in them. The difference is that it's a range of values. It isn't just male or female. Each bar represents a range. And you could actually change the look of the chart, the histogram, by changing the width of those bars, right? In other words, if those bars represent 10 years each, it's going to look quite different than a bar that maybe represents 2 years each. Right? Might even be some bars that don't have anybody in them. And a box plot. I'm going to hold off on box plot. That's used for numerical variables because it's a little bit more complicated. It's better if we actually have a picture. Okay, and there's a lot of information that we're going to be able to get from these plots and these tables, these charts that we're going to produce, that'll help us out. That once we understand them, when we look at them, it'll really help us understand the data. Okay, so first one, simplest one, is called a dot plot. So this is basically, these are whatever these numbers represent. Could be, this is 200 pounds maybe, right? Weights or something like that. So there are 4 people that are 200 pounds and there are 3 people that are 210 pounds. Or actually there's probably some binning. In other words, these are really histograms, right? So they could be histograms. They could be just, if this were discrete, then these would be integers, but it's probably some binning going on here. 200 pounds. This could be 210 to 220. These could be 220 to 230, and so on and so forth. Okay, but each dot represents an observation, a person, a test result. So here's an example of our histogram with weights. So this could be 100 to 110, 100 to 109.999. This is 110 to 100, and so on and so forth. Actually, this is 100 to 150. Each one of these is kind of an odd grouping, right? It's about 33 each, right? 33 and a third each.
Professor,
Yes.
on one of the questions on the homework, it said, how do you tell the percentile on the histogram?
Oh, okay. I'm going to get to that. I'll pull that up. When we get through this, I'll pull that up and we'll talk about that, because there were a couple of things that probably first thing you looked at on those problems on the assignment. Okay, so here, so you can see, like I was just telling you, that the effect of bin size can make the distribution look different. Okay, but they all describe something pretty well. Okay, interpreting histograms. You may notice that a lot of histograms have a certain kind of shape, right? Very frequently, we're going to find we're going to be dealing with data. When you look at the histogram, it's going to have a shape where most of the values, the highest bars, are going to be in the middle. And then as you get away from the middle, the bars are lower and lower and lower, right? So why does that happen? Well, for instance, say a numerical variable like weight, right? Most people are going to be in a certain range of weights, right? As you get people that are lower and lower and lower weights, you're going to have fewer people that are going to be at those extremes, or higher and higher and higher rates. Most people are going to be in the middle somewhere. So, and as you get away from the middle, you're going to find fewer and fewer people within each one of those bins. Okay, we're going to notice later on that often that distribution, that histogram, is fairly symmetrical, right? So, and in fact, we're going to notice that kind of got almost like a bell-shaped curve, right? We're going to talk about that till we die in this course. Okay. Sometimes, however, you'll see a situation where it'll be a whole bunch of people in the middle and then a few over here, but then at the high end or at the low end, you get people that are really low or really high. Birth weights for infants. Okay. Why would you have a situation where you have most of the babies in one area, but then you have some babies that are a far extreme in birth weight? Premature babies, right? If the average birth weight of babies is, I'm going to make up a number, 8 pounds, right? You get some babies that are 9 pounds, 10 pounds, 11 pounds, even 12 pounds, right? But on the other end, you're going to get some babies that are 1 pound, extremely different, as far away from the average, right? So that's an example of a distribution that's called skewed, right? It's not symmetrical. It's pulled to one side, either lower or higher. And we'll get into that. Okay, so skew. Basically, it's our histogram or a representative of a histogram is not symmetrical. In other words, it's not a mirror image if you flip it over the middle. This one is skewed to the left. That's like the premature infants that I just described. There's going to be a small number that are going to be very low weight. There's going to be a small number that are high weight, but not as extreme as the other side. So the left tail is longer than the right tail. That's called negatively skewed, left skewed or negatively skewed. You can see that because it's to the left. It's on the negative side of a number line. This one is right skewed or positively skewed. In other words, the numbers are higher or more positive than for the ones that are the extreme values. Okay, incomes, right? With premature babies, for instance, lifespan, for instance, skews to the left, right? Because there are very few death. Infant mortality in this country is very low, but as people get older, you get more deaths. So life expectancy is left skewed. On the other hand, incomes in this country, right? This is the 1% over here, right? We can see them up here. Right, there's Donald Trump. He's over here. There, there's Bloomberg is over here. He's somewhere. We don't know if he's more than him or less than him because you never know with these guys, right? So at any rate, I haven't checked Forbes to see where they are relative to one another, right? But they're up at this end. So what happens there? If you ask someone what the average income is in the United States, right? Well, before I ask that, if you ask me what the median income, the middle person's income in the United States, it's going to be, this represents an area, right? It's going to be pretty close to here, right? Because most of the values are over here. Very few of them are over here. So the median income is going to be somewhere over here, maybe not too far from where this arrow is, right? A little, not right in the middle of this, right? Because we know these people, there's more people on that side, but a little bit maybe over here or something like that. However, if I asked you what the average income was, the high incomes, the very high incomes that these people have here, pull the average up. So what happens if we have a distribution which is symmetrical? The median and the average, the mean, are in the same spot. They're equal to one another. But if we have a skewed distribution, what happens there? What happens is the median doesn't change much, but the average is pulled away from the median. So the average, when a positively skewed or right skewed, the average is pulled to the right or positively away from the median. And for a negatively skewed, the average or mean is pulled to the left away from the median. So the means and the medians diverge if you have a skewed sample. Okay, now the other thing is shape is important to us. Remember, a lot of statistics that we're working on is going to be based on this idea that if the differences are random, if the differences are not due to some weird thing about the nature of the measurement, like income or like whatever the other one was that was on there, if it's not due to something about the nature of that, most of the time, if weight, whether or not you weigh more than the average, less than the average, if that's due to chance rather than some specific nature about weight that would skew it, then we would expect this distribution to be symmetrical, right? Like that. In other words, a bell curve. Sometimes we'll get into a situation where we have clusters of more people or less people and more people that have those values. In other words, there isn't one peak, there's more than one peak. That's called multimodal. The middle, the highest value, the most frequent value in the distribution, the highest a peak in that curve is called a mode, M-O-D-E, right? So this is multimodal. It has two modes, right? Two high points here, right? And that's called also called bimodal. Okay, so now where could that happen? Well, how about if I took the weights for everyone in the CUNY system, right? Had everybody write down their weights, and I displayed them as a histogram, right? Do you think they would be symmetrical like this? Would you think it would be a bell curve like this? Or do you think it would be bimodal? Yeah, why do you think it might be bimodal? Why would there be two groups, two areas in that curve where you get like peaks? Right, the average weight for women is going to be different than the average weight for men, so it's likely it's going to look something like that, right? That's likely to be a bimodal distribution, right? So you got to keep that in mind. It's not really a normal distribution per se. Outliers. A lot of times we have a situation like in this situation here. Notice again this frequency, right? That means that between 45 and 50, 45 and a half, 47 and a half, and 52 and a half, there were 24 people, for instance, right? That's what each one of these histogram bars represents. Now you notice that predominantly all of our data is clustered around this kind of semi-normal distribution. But then there's one person that's up here at 100, right? Well, a lot of times you'll consider that guy you refer to that as an outlier. It's an observation that's so different, that deviates so much from the rest of the observation that you have to question it. You say to yourself, well, what does this imply? Does this, do I need to handle this in a special way? Did I mention to you like the average, like mean and median? Usually we go for example, if you go out and you get a job and the average salary in this class is, the mean salary is $70,000, but the average salary is $400,000. Well, what happened there? What happened there is somebody that's 7'6" in his class got a job with the NBA, playing center for the Knicks, and he's making $5 million a year. Wait, center for the Knicks is probably more like $25 million a year nowadays, right? Right. So the median hasn't changed. The middle value hasn't changed much, right? It's not sensitive to outliers, but the average is very sensitive to outliers, right? So we'll keep that in mind, that average sensitive to outliers. So we got to really be careful with outliers. Yes.
The graph you talked about, like unimodal and bimodal. What if there's not really any trends? It's just kind of all over the place. We're studying something called parametric statistics. Parametric statistics usually deals with something that involves normal distributions. This kind of normal, based on probability distributions of numbers that are higher and lower than other ones. When you get into situations where the data that you're dealing with doesn't follow those rules, you got a problem. You deal with another kind of statistics called non-parametric statistics. Hopefully, you guys will never have to deal with that in your lives. It's a whole nother, ball game, right? A whole nother set of rules, right? So if you guys taking PH750, that suggests to me most likely that you guys are taking this as prerequisites for EPI courses and other nutrition courses and so on and so forth. You're not necessarily taking it because you're as a prerequisite for taking four more advanced biostatistics course, right? There is another version. It's called PH751 or 755 or something like that, which is basic fundamental biostatistics, but it's a little bit more a lot more theory in it, a lot more equations and theory in it, and so on and so forth. Because the people in that course taking the same material, but they're taking it in a bit more depth, and they will probably be exposed a bit more than non-parametric statistics. By the end of the semester, we'll bring it up so that it'll come up, and we'll talk about what happens. How do you recognize it? What do you do when you deal with that? Okay, so
Now, there's another way to display data, which is called a box plot. So here's a histogram down here. But remember, basically, a histogram is, I know I'm running a little long here, right? Let me just see how many slides I got here. What am I up to? Ooh, I got a long way to go. Okay. Let me see that again. 215. I'm gonna go on for another about 10 minutes or so, and then we're gonna take a break. Maybe we'll take two quick breaks today. Okay, so box plots. Box plot is a special way of displaying data, right? In a box plot, what we're doing is we're taking that histogram that we have, and in this case, it's not shown as a histogram. It's shown kind of as a curve that kind of fits the histogram that's underneath the whole thing, right? And the way it's displaying the data, now keep in mind, this could be a histogram just as well as it could be a curve like this, right? The way that this is displaying this data is that the lowest values are represented by a vertical line, and the highest value is represented by a vertical line. And from the lowest line to the highest value is called a range, right? So now, this heavy black line in here is not the mean, it's the median, the middle value. This really represents percentiles, percentage of people that are between each one of these markers. So between this little feather over here, this little skinny vertical line, and the beginning of this box is 25% of the people that are below it. That's called the 25th percentile, right? Remember, you took the GREs or the SATs. In addition to your score, you also got a percentile. In other words, they told you, oh, your score was 1450. I don't know what the ranges are anymore in this stuff. Your score was 1450, and that puts you in the 82nd percentile. That means 82% of the people who took the SATs scored below you, 18% of the people scored above you. So the lower 25% are represented by the difference between this point and this point. And the median represents the 50th percentile, middle person by definition, 50th percentile. So, and then this next box represents the 75th percentile, right? Now the number of people, or the difference between the 25th percentile and the 75th percentile, what percentage of population does that represent? 50% of the population, right? That's called the interquartile range, the middle two quartiles, right? Those are called quartiles, 25%, 25%, 25, and 25. So that's the interquartile range, right? So that's the middle 25%. That gives you a feel for where most of these values are. So a lot of people tend to like using box plots because they're very descriptive in terms of percentiles. There's a few other advantages that we're going to notice about them also. Okay, just as an aside, when you use Excel to calculate the interquartile range, and when you use SPSS, like in the data, some of you may have noticed this in the homework, when you use SPSS to calculate the interquartile range, they get two different numbers. The reason for that is they use a different technique to calculate. In Excel, I believe I think this is true. I don't remember exactly. I'll give you an example of why they might be different. I'm not sure that I'm describing it without actually describing it accurately, but it doesn't really matter. They just use different. Excel, if you had 12 numbers, sample 12 people, the way Excel calculates the median is it just takes the middle value. 12 people, it just averages the sixth and seventh person, right? And then to find the 25th percentile, it just takes the middle between where it found the median and the lowest value. That it calls that the 25th percentile. SPSS, on the other hand, takes that sample and it calculates a mean and a standard deviation for that sample that it predicts would be the mean and the standard deviation for the population if that were a representative sample, right? If that were truly representative. And it calculates it differently based on the normal distribution, the way normal distribution works. Like down here, you can see that actually normal distribution doesn't really fit this model too well, does it? Right? So, and an outlier over here would be a value that's way outside of these other values. SPSS, when it calculates outliers, what it does is it uses, you can change the rules. You can select a rule for SPSS to tell you when a number is an outlier. By default, what it does is it takes this range in here, right, between the interquartile range. Let's say that that's 10. Like this was 12. Let's say this is 0. No. Let's say this is. I don't want to apply numbers here. Actually, let's say the width here is 10, a value of 10, right? It considers anything to be an outlier that's outside of 1.5 times from the 25th percentile or the 75th percentile, 1.5 times this interquartile range. So anything that's 12.5 more than the 75th percentile is considered an outlier. There doesn't happen to be any values that satisfy that, so there's no outliers at this end. But at this end, it takes, this is 10, it takes anything up, 15 rather. 1.5 times the interquartile range, 15. Anything that's 15 more than, that's more than 15, it would consider that the end, put that leaf there, and then tell you anything beyond that is an outlier. When you use SPSS, you'll see how that works. Why are these so nice? They're so nice because, for instance, if you put them side by side, it makes it really easy to see where the median is, where the mean is, where the median is, what the range is, how narrow the distribution is, how wide the distribution is, right? So, for instance, you can see that the median here is much different than the median here, right? The ranges are similar. You can see there's a lot of outliers at the low end for females and so on and so forth. Maybe these are weights, for instance. Maybe there's not more underweight females than there are underweight males, perhaps, right? What can you tell me? See, notice this median here is not in the middle. What do you think that might tell me? Right? You would expect the median to be right in the middle, right? Because it's the middle person, right? 50% or below, 50%. But this one's to the left, right? What does that tell you about this distribution, you think? It's right skewed, right? See, there's values that are pulling a lot of this away from the median. So the average would be pushed to the right, right? So that's right skewed. If you drew the normal distribution, probably look right skewed. Okay, mean, median. So numerical variables. How do we describe numerical variables? Mean, median, and mode. They're all measures of the central tendency, of the middle. Yes.
So you said 15 more. You mean points and percent?
Yeah, don't worry about it. What I'm saying basically is that SPSS uses a certain rule to decide whether a number is so far out that you should define it as an outlier. Okay, but SPSS is not the law. SPSS follows your instructions. That's its default. You could change that, but effectively what it really means is that it's up to the researcher to decide whether an outlier is an outlier because it really doesn't represent your data appropriately, or if you need to really include it because it really is part of that population. That's a decision that you have to make based on a number of reasons. But mathematically, programs like SPSS, they will calculate it and suggest outliers. Up to you to decide how to deal with them. Quartiles, percentiles are another way of describing numerical data. In other words, especially with box plots. Range, lowest to highest. Another way. Standard deviation, we calculate 2 weeks ago. Seems like another lifetime, I know. Remember we used Excel, we calculated standard deviation. X, we found the mean, each value minus the mean, square that, take the sum of all the squares, divide by n minus 1, that's the variance, take square root of variance, that would give you the standard deviation. Standard deviation is a special measure of the spread. So the first three things here, mean, median, mode, give you an idea where the center is. Everything else is basically gives you an idea of how it's spread out. Okay, one little bit of ugly stuff here. Okay, here's the mean. Now we know how to calculate the mean, right? Just take all the values, divide by the total number of values, the count, right? So what is this saying? X bar. So immediately see X bar. What are we talking about? Population or sample? sample, right, is equal to, and I'm going to take sigma is pretty much universally in math. Sigma means the sum of, right? So this is a sequence, the sum of all of the x's. Usually xi usually means that you're going to apply these numbers here. I starts at 1 and goes to n. N is the number of values. So if you have 36 subjects, each one of those subjects, x for the first subject, x for the second subject, x for the third, x for the first to the 36th, in other words, subject. You're going to take all of them, add them together, and divide by 36, right? 1 over n, right? 36. Okay, so that's all that really means. So hopefully we'll avoid too much of that stuff. It really doesn't. Uh, some of it's important to just recognize and understand, but once we get past all of this, you're really not going to be looking at that in terms of applying it. You're going to be using various programs to apply it. The mean is not resistant to outliers. The median is resistant to outliers. Argument there was, again, let's say, I think I have an example of this. There you go. 7 dwarfs, right? The median, let's say that average salary is 50,000, right? If somebody joins that group, that sample that makes $1 million, median doesn't change much. At most, it just changes one person higher or lower, right? The average, though, is going to be drastically affected by that. Mode is the value that occurs basically most often. You got to interpret that a little bit. This is bimodal, for instance. That's the mode. You might consider that bimodal. Maybe not. It's a close call. And then skew, we already kind of talked about skew. Percentile. One of the things we're going to notice is that the bigger and bigger sample that you take, and the narrower and narrower that you make those histogram bars, the closer that your histogram is going to come to looking like a curve. So like instead of big wide bars here, if there's many very narrow bars, it's going to start to look like a curve. Those are going to kind of connect together and look like a curve. The areas underneath those curves are going to represent the percentage of values there. Like for instance, here, if you look at the chart on the right, if this is a distribution of people's weights, 90% of the people, well, let's say this is an SAT score, right? This is distribution of all the SAT scores. 90%, the area here represents 90%. This area only represents 10%. It's going to be important to us to interpret these charts this way as we move forward. But basically here, we can see that 90% of the scores are below 1,200 and 10% of the scores are above 1,200. If I move this bar over and that dark red area becomes smaller, if I move it over to 1,300, maybe 5% of the scores are above 1,300 and 95% are below 1,300. But the area represents the number of scores, number of people, number of scores, and so on and so on, number of observations that are there. Now, if I were to divide this, if I would find the median, that is a little bit skewed, so the median would be a little past here, right? If I drew the median here, then you would know that the area to the left and the area to the right are equal to one another. So that's why you wouldn't be just in the middle of the top here, right? Because then this area would be bigger. So the median is a little bit to the right of this, right? Quartiles. Similarly with quartiles, see quartiles divided up here. Each one of these represents the same area underneath this curve. Again, it's skewed a little bit. Hopefully, we don't wind up with too much skewed data. Range is the minimum to the maximum. Okay. The variance, again, another ugly formula. Again, we'll just interpret this formula. You're not going to be tested on this formula. Okay, how does this work? Well, summation, that means we add them all together. What are we going to add together? We're going to add together the difference between each value. Again, sample 36, sample size 36. That would mean we have sample number x1, x2, all the way up to xn, number 36, x36. We're going to take that value, subtract the mean from it, right? That's the difference between the mean and each individual value. We're going to square that value. Now we got the square of the differences between the mean and each individual value. We're going to add all 36 of them together. We have the sum of the squares of the differences between the means, which we did with Excel, right? And then what are we going to do with that? We're going to divide it by n, right? And we're going to call that the variance. Actually, I told you that there's a reason for this. We'll discuss it later. We use n minus 1 instead of n. It turns out to be a better estimation of the variance than this is actually called degrees of freedom when you subtract 1 from it. We won't worry about that right now, but you divide basically by n to get the average square, the sum of the squares of the differences, right? And we call that the variance. They notate it as s squared here, right? Because what we're going to do next is we're going to take the square root of this whole thing. Here we go. We take the square root of this whole thing that we just did before that, right? And we're going to call that the standard deviation. We use the letter S here because it's the standard deviation of the sample, not the population. For the population, it would say sigma, right? So there's S squared is the variance represented by that formula, but that's where that formula comes from. That formula describes what we did when we I think I record. I'm sure I recorded that, so you could go back and look at it if you want from last week. Okay, so I'm not going to go into this too much, but this is the way the squaring and square rooting and stuff like that affects the distribution, if it's normal distribution or not a normal distribution, and so on and so forth. I think that's getting a little bit beyond what we really need. Okay, so standard deviation. The standard deviation, let's think about, we're looking at the mean and the median. Those are two most important ways of describing the center. From now on, we got range, we got other stuff and stuff like that. However, it's going to turn out standard deviation is going to be the most important way that we describe spread or variability, right? So we know that mean is not resistant to outliers. Median is resistant to outliers. We'll have a standard deviation. Think about how we calculated the standard deviation. We looked at the difference between each value and the mean. So if there's a big difference between a value and the mean, the next thing we do is we wind up squaring that. So it blows up that difference. So as it happens, because of that blow up, whenever we have like big differences between the mean and any value that's far away from it, the standard deviation is not resistant to extreme values or outliers, in other words, right? So you got to be careful with the mean, and you got to be careful with the standard deviation when you have a distribution that's not normally distributed, that's skewed. Okay. Okay, well, the alternative measures of spread, interquartile range, we looked at the range, median, absolute, nobody uses that. Don't worry about that. Okay, I think we're about done here. We can take a break without having to worry about coming back here. But again, we'll take a look at all of these things moving forward as we do these calculations. Dot plot, histogram. We're going to look at something called a leaf plot, which is SPSS produces, which is very much like a dot plot. Mean, median, mode, our central tendency, percentiles, quartiles, right, and our interquartile range, standard deviation. The way we calculated the sum of squares, unimodal, bimodal, multimodal distributions. We looked at skew, left skew, right skew, positive, left is negative, right, also called positive. And we talked about what might happen when we have to deal with outliers. Okay, so we're going to move on and we're going to actually do some of the work here. We're going to create some histograms. We're going to calculate some of these statistics. And this is going to go a long way to helping you with some of the issues that kind of scared you on assignment 1, right? Okay, for those of you that got scared on assignment 1. Okay, let's take a 10-minute break.